Okay, in this video, we're going to be looking at primarily how to determine asymptotes of rational functions. On the example, I'm going to go ahead and graph the rational function just so you kind of see a complete process. So first off, when you're looking at a rational function, that means you have a polynomial on top and bottom. You got to kind of keep straight something about fractions. If the zero's on the bottom, it's undefined, right? If there's a zero on the top, that just equals zero. So first you need to keep that in mind. That helps you keep straight what you do for each of these cases. So the first thing I like to consider is the domain. Okay. Now, to determine the domain, I need to look at the denominator, the bottom part, and find out where that's undefined. So one thing that would really help me would be if I would get this polynomial factored, and I might as well factor both the top and the bottom. So I usually go ahead and get this into factored form. And so I can see the denominator pretty easily because that's just a difference of squares. So it's x minus 4, x plus 4. With the numerator, let me see what I would get. There's a common factor of 2. If I factor that out, I'd have x squared plus 3x minus 4. And then I need to see if that would factor again, and it will, with a plus 4 and a minus 1. So the numerator factors into 2 times x plus 4 times x minus 1, okay? All right, so once I get that thing factored, that's going to help me more easily determine a couple of the features, the couple of the characteristics I need. So domain is what I was asking you about. So domain has to do with where does the denominator equal 0. So that's what you should be thinking. Where is this function undefined? So you're thinking about where is the denominator equal to 0? Is what you should be asking yourself. So we can see in factored form at a glance that x better not be 4 and x better not be negative 4. All right, well, it's undefined at both of those places, but one of them is a bigger issue than the other. And so this has to do with what happens at each of those spots on the graph when we get ready to graph it. So it's undefined at both spots, but notice the x plus 4 could actually be canceled out. Okay, and you'd be left with 2 times x minus 1 over x minus 4 if you were to do that. So back in Math 100, we used to ask you to simplify the rational expression, and you would have put this down as what it would be when it was simplified. And the original expression in that are basically the same, except the original one, or when you look at it in factored form, is undefined at negative 4, where this one doesn't have that problem. So see, we can fix the problem happening at negative 4 by just canceling the x plus 4 factor. All right, that means you're going to have a hole. You're going to have a hole at x equal negative 4. And sometimes you have to write what the coordinates of that hole would be. So there is a way to do that if you got into depth on this. And all you would do would be to look at this place up here where we canceled out the problem, the trouble spot, the x plus 4. And if you plug negative 4 into that, where you've already removed the factor that would have become 0, then you can plug into what's left there and find out what the coordinates of the hole would be. Okay, so the coordinates of the hole would be, let's see, negative divided by negative. So that would ultimately be positive 5/4. I wish I had just written it without that plus. Okay. All right. So what I know is that at negative 4, there's going to be a little tiny hole that I could put a plug in at negative 4 5/4 and 5/4. All right. The vertical asymptote is a bigger problem. Okay, so this one is a hole because it was removable. It was associated with the factor we could cancel out, but the x minus 4 factor corresponds to x equaling 4, and at x equal 4, we're going to have a vertical asymptote to the graph. Okay. All right, so what that tells me are places where the function is undefined. So over here at x equal 4, I'm going to have a vertical asymptote. So the graph can't cross it. Okay, there's no ordered pairs there. And then over here at -4 and 5/4, which is 1 1/4, there's going to be a hole right there. Okay, it's not going to have an ordered pair there. It's going to skip over that. All right, so let's go to the rest of this. So go back to the notes page. And the next thing I look at is horizontal or slant asymptote. That's the end behavior. Okay. And if I'm trying to determine the end behavior of this, I can just use those rules on the notes page. I can look at the degree and notice that the degree on top equals the degree on the bottom. Okay. And if the degree on top equals the degree on the bottom, then I know it's going to have a horizontal asymptote, and I can just take those leading coefficients, 2 on top divided by 1 on the bottom, and I know my horizontal asymptote is going to be y equals 2. Okay. All right, now another thing that works on this is to use division. You could use division here, and you could take your x squared minus 16. I'm going to put in a placeholder for that and divide it into the other polynomial, the one that's on top. I can't use synthetic division because it's squared. So I could do this. Oops. And it would go in there 2 whole times. And when I multiply back, that would be 2x squared plus 0x minus 32. And remember, when you do that subtraction step, it works good to go ahead and change the signs on each of these so that you can think of it as adding straight down. So you'd get 6x, and then -8 and positive 32 would be plus 24. This work right here could be used to write the original rational function in another form, write it as a mixed number. So it would be 2 and plus the remainder over what I was dividing by. Okay. And I'm showing you that because I want to show you a connection later that the horizontal or slant asymptotes come from the quotient. Y equals whatever the quotient is. Okay, not the remainder part, but whatever y equals the quotient is. And that's because it's end behavior. So it's what happens for really big x's in either direction. And if you put bigger and bigger x's in here, this right here is gonna go away. That's gonna go to 0. Okay? Because as the x gets bigger and bigger on the bottom, it gets bigger faster than the x's on top. And so y equals 2 will be your end behavior. Okay. And then this concept of division being the way to find the horizontal or slant asymptote gives me one way that works on all the problems. But the shortcut, I think, is really good to know. So since m equals n, since on top and bottom the degrees are equal, then I can just take the leading coefficients, 2 over 1, and I can get my horizontal asymptote that way. Okay. So that means that I know that right here is going to be a horizontal asymptote. And your graph can sometimes cross it, but doesn't usually. Your graph just approaches it. Okay, and then x and y intercepts are old business. An x-intercept is when y equals 0, and a y-intercept, you let x equal 0, and then you just work it out. Okay, so if you think about letting y equal 0, you're trying to get the whole entire rational function that you started with to equal 0. And to get it to equal 0, the numerator would have to be 0. Okay? And so, because that's the way fractions work, for fraction to be 0, the numerator has to be 0. So really, you can just look at the factored form right here. And since you have an x plus 4 and an x minus 1, the x-intercepts are going to be at x equals -4 or x equals 1. And we're really talking about the ordered pairs, -4, 0, and 1, 0. Okay? Except this one was tricky. Okay, normally that's it, and those would be your x-intercepts. Except you need to be careful because an x-intercept has to be a point that's in the domain of the function. And so when you think that, you need to double check and think, okay, but wait a minute, -4, the -4, let's see, that was not in the domain. Remember how x couldn't be -4? So I have to rule that one out. And so your only x-intercept happens at x equals 1. Okay. Another way to think about it is you can let y equal 0 on the simplified version to find the x-intercepts. Okay. All right. Now for the y-intercept, you let x equal 0. Right. So if you were to let x equal 0, that means you got to plug in a 0 everywhere. And so if you do, you're going to wind up getting a 2 times 0 squared plus 6 times 0 minus 8. I just want to show it to you so you see what happens. Do you see how everything is gone except for the constant terms at the end? And so what you got is really a -8 over 16, which is a 1/2. And so the y-intercept turns out to be 1/2 or 0 1/2. Okay. Now, that's probably all you're going to be asked to do. I doubt we'll go on and get to where we graph them. But I did want to graph at least one of them for you so you could see how I could use that information. Okay, so I know it crosses the x, it has an x-intercept at 1, so I can put that on there. I know it has a y-intercept at 1/2, okay? And I know y equal 2, this right here, is a horizontal asymptote, and x equals 4 is a vertical asymptote. So those dashed lines represent where we don't have an ordered pair. And then this spot right here, this is the hole, okay? So this is the hole, and that was the point that was at -4 5/4, okay? All right, and then if you have just a slight idea of what rational functions do, you know how they kind of split and approach the asymptotes, you might already have guessed what happens here. Because you have more points on this side. Probably does something like that. And then it's going to approach this asymptote. Now, if you really want that to be more accurate, don't forget that you could just, let me make this smaller. Don't forget that you could go back. Okay. That you could go back to the original. If you wanted to know and pinpoint that better, you could go back and just think about plotting points. We're just trying to get a sketch without having to plot so many points. So I could do that, and I could plug a 3 in. And if I did, I'd have 2 times 9 plus 18 minus 8 over 9 minus 16, which would be -7. So I could get a sense of what this is going to turn out to be by calculating that. So let me do it on my calculator. So that's 36 minus 8 on top, which is 28, divided by a -7. Okay, so that's going to be a -4. So if I did want to pinpoint this a little more accurately, I could see some additional points to kind of see what happens. And then I don't see any points over here, but if you did go in and plug in like 6, if you plugged in 6 and worked it out, okay, 6 winds up being all the way at 5 after you plug into the original expression and find the output. So you could plot that point, and you could work 5. When I did 5, it was all the way at 12. And all I did was plug in a 5 to the original function. So you could plug in some additional things. I had to be all the way out at 10. So 6, 7, 8, 9, 10. I had to be out at 10 to even be at 3. So this one comes in and does something like this here. Okay. All right, so we won't do a lot of graphing. We'll just get the key features of it on these other examples. Okay, so let me kind of do several examples showing you how to think through it. And on these, I won't try to graph them on this, but when I save it, I'll have the graph sitting next to it so you can see it. All right, so here's what you do to reason things out. So domain, you should be thinking, okay, that's the denominator. Can't be 0, okay? So what you wind up doing is thinking about the factored form of this. And the factored form of that, if it does factor, let's see, it's +2 and -1, will help you get the domain quickly. So you can see at a glance that x better not be -2 and that x can't be 1. All right, now what issue is happening at each of those depends. So when I look at this, do you notice how those x minus 1s could be canceled out? That if I were to simplify this, it would simplify into 1 over x plus 2. I could cross those out and get 1 over x plus 2. So that means the issue with x being 1 was fixable. I could just cancel out that factor and I'm through. So that means there's going to be a hole where x equals 1. Okay? And then if I needed to know what the y coordinate for that would be, I would plug it in right here. I would plug it into 1 over x plus 2 to where I had canceled out. I would plug the 1 in that I got. Where are my tools? There they are. I would plug the 1 in that I just know gives me a hole, and I would just calculate what I get, and I would get a third. So I know at 1/3 there's going to be a hole. But the other issue, the x plus 2 wasn't removable, wasn't fixable. I couldn't cancel it out. So that's going to give me a vertical asymptote, and that'll be a vertical line at x equals -2. Okay. All right, now when you do the horizontal or the slant asymptote, that's the end behavior. Okay, and that's where sometimes it's good to have this rewritten so you have the quotient plus the remainder over the divisor. So if you tried to divide on this one, the x squared plus x minus 2 would go into x minus 1, and the degree is bigger out here. It's almost like you're trying to divide a bigger number into a smaller one. So it goes in there no times. And then when you multiply back, you'd have 0. And then when you subtract, you'd have x minus 1. So it just turns into 0 plus the remainder over the divisor. Okay. Now you could use the shortcuts for finding horizontal asymptotes. You could wind up just saying the degree on top is 1, the degree on the bottom is 2. So the degree on the bottom is bigger, so you know it's going to have y equals 0 as its horizontal asymptote. Okay, so the quotient, y equals the quotient, is something that tells you the end behavior no matter what the situation is with the degrees. Okay, then if I needed x-intercept, that means I needed y to equal 0, okay, which means the numerator would need to equal 0. Okay, so you might think, oh, I need to set x minus 1 equal to 0, so I get x equal 1. But then you have to remember that, wait a minute, 1 was not within the domain. Okay, so it's not going to be an x-intercept, not in the domain. Okay, and it was the only possibility, so there's going to be no x-intercepts. Okay. All right, and then for a y-intercept, you let x equal 0 everywhere. And remember how on the last one, that just meant all of the terms with x's in them would be gone. And so we get a -1 over a -2. Okay, so it'd be 1/2. And so what we're saying is the ordered pair 0, 1/2 is going to be the y-intercept. Okay. All right, so really I want you more than anything to be able to get asymptotes. Holes happens occasionally, but not that often. And without us being able to do it more deeply, you probably aren't going to be asked about holes very much. Okay. All right, let's try another one. Let's look at number 2. All right, I'd like to have it in factored form because that helps me when I'm getting my intercepts in my domain. So if it's not already and it can be factored, I like to do that right off the bat. So there's the factored form. Okay. All right, you also could, if you wanted to, go ahead and get it written as a quotient plus remainder over the divisor. This one's important because see how the degree on top is 1 more than the degree on the bottom? So you're going to have a slant asymptote, okay, which means you're going to have a line that's slanted, not y equals a number, but y equals mx plus b. And here's how you're going to find it. You're going to divide, but we don't have to do long division. like we did on the others, because this is to the first power. So this is where the synthetic division can help us. So set it up as a synthetic division problem. And remember, x minus 1 corresponds to 1 as a root. So 1 goes in the box. So you bring down 1, multiply, write it there. Add straight down, you get a 2, multiply, and write it there. Add straight down, you get a negative 4. That's your remainder. So that helps us to rewrite this as a quotient plus a remainder over a divisor. So this is my quotient, that's x plus 2, my remainder over what I was dividing by. These always have to match right here. Okay, now here's the thing to think about. So if you're trying to find the horizontal or the slant asymptote, which is end behavior, you're looking for what happens when you plug bigger and bigger numbers in for x, bigger positive or bigger negative. The bottom is going to get super big, and the bigger you get, the closer you get to 0. And what you'd be left with is that. And so your original rational function turns into y equals x plus 2. Okay, so the form that you get after you do your division, either regular or with synthetic, can be used because y equals the quotient is always going to be the end behavior. All right, now domain has to do with where it's undefined. So the denominator can't be 0. So that means x can't be 1. And that's the only issue. And see how there's not an x minus 1 factor on top. So you can't fix the problem by canceling it out. So that means you're going to have x equal 1 being a vertical asymptote. And there aren't any holes. Okay. All right, then for x-intercepts, that's letting y equal 0. Okay. That means the numerator has to be equal to 0. And you have it in factored form. So that's and I'll just write it here, the numerator equal to 0. Domain, remember, was the denominator equal to 0. All right, so the numerator equals 0 when x equals negative 3 or when x equals 2. And both of those are in the domain, so I don't have to rule them out. And so those are going to be my x-intercepts, and you can write them as an ordered pair if you needed to by putting a 0 there at the end. It's acceptable usually both ways. All right, and then for the y-intercept, you're letting x equal 0. And remember, that knocks out all the terms that have x's in them. And so you basically are left with negative 6 over negative 1, which is 6. So your y-intercept is going to be 0, 6. All right, so that kind of covers a lot of the important features of that particular rational function. All right, let's try a couple more. All right, on number 3, for domain, it's denominator equals 0. So that would be, where does 3x plus 9 equal 0? And that happens when x equals negative 3. Okay. And then that is not, like if I wrote it in factored form, I would have an x plus 3 down there, but I can't factor the numerator. So that negative 3 is a problem that can't be fixed. So it's a vertical asymptote, and there are no holes. Okay. For end behavior, you could use the shortcut on this if you wanted to, since the degree on top and the degree on the bottom are the same. Okay. The m equals the n is what we said on the notes. You're going to have a horizontal asymptote, and the shortcut for it would be what you have as the ratio of the leading coefficients on the top and the bottom. So y equals 2/3. And it was because the degree on top and bottom were equal. So you could just take the leading coefficients. You could do it with division, but that's kind of a challenge to do. But 3x would go into 2x. It'd be kind of hard to understand this unless you're pretty good with fractions. Goes in there 2/3 times, and when you multiply back, you get 2x plus 6. Then when you subtract, you get a minus 11 there. And that would be a way you could have written this in quotient plus remainder over divisor form. Okay, and then that would go to 0, and so you'd see a horizontal asymptote at y equal 2/3. Right, and then the x-intercept is where the numerator would equal 0. So you take 2x minus 5 equals to 0, and you get x equals 5/2. And if you wanted it as an ordered pair, that would be 5/2, 0. And the y-intercept, you're letting x equal 0. So you're getting rid of the terms with the x's in it, and what you have left is just negative 5/9. And sometimes we just say negative 5/9, and sometimes we put it as an ordered pair. All right, so I just want to do several of these. All right, I got one more now. So on this one, the degree on the bottom is bigger. Okay, so when I get ready to do my horizontal or slant asymptote, it's going to be horizontal. But see how it's bigger? If I were to do the division, I couldn't use synthetic. If I were to do it, it's going to go in there 0 times. And so, it would turn out to be 0 plus x over x squared minus 3x minus 4. So again, the quotient is what gives you the end behavior. And in this case, it would be y equals 0. And that approach works on all of them. It's just that we don't always like to do the long division to find it. All right, now for domain, I would like to have this factored. So I'm going to take a moment to factor the denominator. It's x minus 4, x plus 1. Domain has to do with where the denominator equals 0, because you can't have that. And so you can see when it's in factored form that x can't be 4 and that x can't be negative 1. Right? And neither of those are fixable. Like you can't there's not a factor on top that you could cancel out with. So those are both vertical asymptotes, the vertical lines at x equal 4 and x equal negative 1. And again, no holes. Then the x-intercept is what causes the numerator to equal 0. And that would be x equals 0. Right? Because to make y equal 0, the numerator would have to be equal to 0. And 0 is in the domain, and so that would be your x-intercept, or you could write it 0, 0. And for the y-intercept, we let all the x's equal 0. Okay. Now when we do that, everything's gone, so we get a 0 on top when we let x equal 0. Okay. And we wind up with a 0 on top, and we wind up with a negative 4 on the bottom, but that equals 0. So the x-intercept, it's also the y-intercept because it's right there at the origin. So I won't bother graphing in the video, but when I go and scan this to post, I'll go ahead and draw a graph for you at that time. Save it. Okay, so I'll just say that. Okay. Oops, meant to stop the video.